Greetings everyone. I am Uday Sharma from the AAA Department of Institute of Aeronautical Engineering. Today, I'm going to discuss about complex functions and its applications to electronic and electrical engineering. This program text or this program is an introduction to the algebra of complex numbers to engineering students, particularly because of its relevance and important problems of applications in electrical engineering. It is designed for a person who is well experienced with algebra of real numbers and calculus, but who has no experience with complex number algebra. The brain idea of this text is like, or this idea is origin of complex numbers, graphical interpretation of quadratic functions. So solutions are complex numbers, fundamental operations of complex numbers, exploring finding the nth root of the complex number, differentiation of sin x and cos x. Complex numbers have important applications in many fields of engineering, particularly electrical engineering. Parallel in the case of real numbers, is an algebra of complex numbers such as calculus. In the electrical literature, it is customary to use J rather than the universal used I for mathematics literature, as I represents ampere slash current in electrical engineering, and J is called the imaginary unit. And the name would have been better, but the numbers are like 2J, 3J, etc. Like if we take a graphical representation in an electrical system, the numbers are called the real parts, and this is the imaginary line. The numbers on this are of minus 1J, 1J, 2J, etc. In circuit theory, complex numbers can be used as a model influences, which is impossible using real numbers. In a special case where all the elements are resistors, it could be attained using real numbers. But when there is also capacitors, the solenoids or theoretical approach can be reached using complex numbers because of both magnitude and phase. In addition, I would say that the alternating current power sources can also have a complex numbers representation. This allows the analyst to use precisely the same producers for modeling passive AC circuits as are used in the resistive circuits. The methods are algebraic or algebraic. Now, I would hesitate to point out that this complex number method assumes everything is steady state. You have this asymptotic behavior, like it is not continuous, it follows a steady state. If you need to analyze the transient behavior, you need to solve the D's like chronics. The same way, imaginary numbers are not useful for counting objects in everyday life, but they are essential to concrete applications in various areas of engineering and science, such as signal processing, control theory, electromagnetism, vibration analysis, quantum mechanics, and others. Like if you take in control theory systems are transformed from time domain, frequency domain, using Laplace transforms, where Laplace transforms are part of complex analysis. Complex numbers are used in signal analysis and other fields to obtain a convenient description of signals that vary periodically for given real functions that represent physical quantities, often in terms of sine, cosine. We consider corresponding complex functions of which the real parts are the original quantities. For a sine wave of a given frequency, the absolute absolute magnitude of the corresponding number z is the amplitude, and the argument is the phase. Like if you can consider this is sinusoidal waveform, the magnitude is the amplitude and the argument is the phase of the system. It also considers or falls into the part of a complex analysis. The residual theorem is a complex analysis, is a powerful tool for engraving the path integrals of memoraphic functions with respect to closed curves and can often also used to be calculate real integrals. In electrical engineering, the Fourier transform is used to analyze varying voltages and currents. Treatment of resistors, capacitors, and the inductors can be identified by introducing imaginary resistors that are frequency dependent and combining them into signal complex numbers called as the impedance. Like if you say the Fourier transform is used to analyze varying voltages. The Fourier series as simply can also as a series a part of complex analysis, and it is used to measure the impedance. This is also used to extend to digital signal processing, digital image processing, which uses digital versions of Fourier analysis to transmit, compress, and restore image, auto, or video signals. Electrical engineers use the letter J for the imaginary unit as it is typically reserved for the varying units. Like we know as discussed earlier, J is imaginary in the electrical, as mostly I is considered as current. Instead of taking the magnetic and electrical paths into real numbers, we can represent it as a complex number. For applied fields such as engineering, complex numbers are often used to calculate improper integrals and real-life values using complex numbers functions. When the complex number is a purely imaginary, such as the real part of 0 and the imaginary part of 120, this means the voltage potential of 120 volts and a phase of 90 degrees, which is completely real measurement. Like we use these kinds of measurement phase and voltages using the complex analysis, and we measure these values using this complex analysis. So we can finally conclude that the complex analysis is a part and it helps a lot in calculating the values and calculating different theories in the electrical and electronics engineering. Thank you. This is Adesha Sharma signing off.